There we go. Then we can make a proper start. Okay. So yeah, we'll as I say, update the questions and answers into the documentation. Um, so there's a question already actually, which I just kind of want to come to, which is nice and timely. Um, the background to this is that we very much believe in community education. So our background has been we've run workshops for many years. We used to run these in person in London, teaching about blockchain and zero knowledge. And we are very passionate about these areas of technology, and we want to be able to share that. But there is, I think, quite a few people find particularly zero knowledge proofs quite daunting because of the maths involved and because of the terminology, it can be very difficult to get into. And that's a great shame. I think there's a lot that it's an area that's going to be very important and people can gain a lot by understanding it. And so, yeah, my motivation is to try to help people with that journey really to help them so that they can get a better understanding of the technology. I've given this talk at various conferences, most recently at ETH Zurich, and well, I think I'm going to be doing it at ETH Prague as well. So it's an ongoing thing, but one of the reasons we wanted to do it, well, we wanted to do it on YouTube, was just to give myself more time, really, because we don't usually have much time at a conference to go into it in much detail. Yeah, so in terms of what we're going to cover today, I'm really trying to cover the background. So I'm not going to say very much about zero knowledge proofs themselves. It's really to try to cover the maths that you need and some of the concepts you need to understand when you're starting with zero knowledge proofs. But I'm not going to go into a lot of detail about the proofs themselves. Okay. If you want to get in touch with us, there's some details. There's our social. You can, if you join our Discord server, then we provide updates on the courses we're running. Sorry, that link there. Well, the notes are pretty much the same, but that is slightly out of date. This link here is the best one to follow for these notes. Okay. So one person who is very much involved in this scene did some good quotes, which I like to start with, to say that yes, this stuff is hard to understand, but it's not your fault if you don't understand it fully. And please persevere if you don't understand it. It can take a while to get used to some of the concepts and some of the ideas, but it's well worth making that effort. And it is understandable at some level. And I really want to stress that it is possible to understand a lot of these concepts. So please don't give up. Please keep trying. But don't try to understand everything at once. It's a good idea to take things in small pieces, get familiar with some of the terminology, and maybe chunk some of the ideas and some of the topics. So you can, if you see a particular idea that is going to go into, you need to go into depth about, well, maybe just treat that as a kind of a chunk that you'll come back to later, and do it that way around. That will help you learn it and get to grips with the whole area. So one of the areas to start off with is around some of the terminology and some of the symbols you need to see or you need to understand. If we're looking at numbers, there are different sets of numbers that people have put together for various reasons because it's useful, and they use special symbols to refer to them. So, for example, the integers are referred to by this Z with a double slash, rational numbers by a Q, etc. And the ones we will be using mostly in zero knowledge proofs are the integers, so the ones represented by the Z. We also have this symbol F to talk about a thing called a field, which I'll come on to. And we have a special a special set of integers, special set of numbers that we use, which is represented by this Z with an asterisk and a P. And I'll come back to what all of that means in a moment. And we do this. We use these special sets and these things called fields because they are useful, because they allow us to do bits of cryptography and to do it in a a way that is relatively easy. It also gives us, it simplifies some of the maths and gives us short representations of things. When we're dealing with integers, it is easier to deal with those than, say, rational numbers when we're doing certain types of operations. Okay. Now, a lot of the operations that we do when we're doing we're using zero knowledge proofs is using modular arithmetic. And if you're a developer, then you may well have come across this. If not, one of the easiest ways to think about it is to think of it in terms of a clock, where it's often called clock arithmetic or clock maths. The point about it is that we're very much interested in the remainder of some operation. So if you're thinking about a clock, you'll move the hands around the clock. You're you're often not interested in how many times round the clock you've gone. You're more interested in where the hand ends up pointing. So this is the remainder that you get when you do an operation. And if we use the mod operator, then what we mean is that we're thinking about the remainder when one number is divided by another. And so for example, if you take the number 25, you do mod 3, the remainder is 1, and 15 mod 4, the remainder is 3, and the remainder is going to be positive. Okay. Now, I think that's fairly straightforward and self-explanatory, but we do rely on that quite a bit when we're doing operations. But what I'll come on to now is some theory that is a little bit more abstract. It's not, I don't think, particularly difficult, but it's not typically taught at sort of the school level maths that people do. I suppose because it is quite abstract. You probably don't need to know it so much, but it is something that we do need when we're looking at the cryptography we use for zero knowledge proofs. Okay, so your background is math, so this is probably very familiar to you then. Okay, but I'll go through it also for the recording. So if we think about a group, what it is a set of elements. And these elements could be anything really, but in our case, we're going to be talking about numbers. And then additionally, we have some binary operation. In these notes, I'm representing this as this dot, and we can choose this set of elements and this operation however we like. But if it is going to be a group, then it has to have certain properties, and these are the properties listed here. I guess one of the most important ones is this first property, is this idea of closure. And what this means is that if we take two elements within our group and we do the operation on those elements, then we want the result also to be within our group. And that kind of makes sense, because that's, otherwise we wouldn't really know how to handle, the result of the operation if it was not within our group. The next one is around the ordering of things. That's sort of not as interesting, and it's just but fairly straightforward. And then the next two are important. The first one is the idea that there is some identity element within our group, so that if we do an operation, we do it between one element in our group and the identity element, then this doesn't change. The result we get back is the original element we had. The easiest way to think about this is if you're thinking about when you're multiplying a number. If you sort of traditional multiplication we do, say with real numbers, if you multiply by 1, that is the identity element, because the result you get is just the number that you started with. So that's what an identity element means. And then for an inverse, what we're doing is we start with some element within our group, and we're trying to find another element that, when we do this group operation between these two elements, our original element and the inverse element, we get back to the identity. So if you think about, if you're thinking about, say, addition within, say, with real numbers, then you the inverse for a positive number would be a negative number of the same magnitude, and that would get you back to the identity element, which in the case of addition is 0. So fairly simple concepts, I think, but these are the things that we need if we are going to have a group. Of course, when we're creating a group, it could be the case that the elements we've chosen, this set of elements that we're going to have as our basis of our group, could actually have a smaller group within them, and that is a subgroup. So that is possible. You could have those, and then we also have the possibility of a cyclic group, and these involve generators. And what a generator is that if you start with this generator and then repeat the group operation, eventually that will take you through all the elements within the group, and bring you back to the start. So as the name suggests, it's a way of generating all of the elements within our group. Okay, now that's a sort of very basic concept, I suppose, the group. We can take it a little bit further and produce what is called a field, where we have an extra operation, and we usually call these addition and multiplication. That's the easiest way to think about these things. And so they also have the properties that we need for a group. So again, we want the idea that we have a way of we have some kind of identity element within our field, but we would need one of those for addition, and we need one for multiplication. So the sort of easiest way to think of those: for addition, the identity would be 0. For multiplication, that would be 1. And again, we want inverses for those operations. So if we have the operation of addition, then we want a way that we can, for a particular element, we can get back to our identity element. And similarly for multiplication. Because we have different operations, then we have this idea, this sixth point here of the distributivity of the operations as well. And one point that you find when we're thinking about fields is that if we're thinking about this, all the traditional types of arithmetic we do, we're used to using multiplication, and we tend to think of division as being a way of getting to the inverse of multiplication. One of the problems we may find is if we start with our element, if we start with a set of integers, then division becomes a little bit more problematic, because when we're dividing integers, we may end up with something that is not an integer. So this would break our closure rule. And so if we're building a field and we're doing this from a set of integers, then we may need to we may specify that we want an inverse for multiplication. So we want a way for the multiplication operation to work and for us to get back to the identity element. But we may have to have a special way of doing that. So just addition and subtraction, multiplication are more straightforward, but division tends to be more difficult. Okay. And again, we can have generators within fields as well. If we talk about a finite field, what this means is that the set of elements that we are starting with is finite. So there will be a highest number within our set. And what we usually do or what we often do, is to have a prime number. And we start with a set of integers, and we do arithmetic mod that prime number. And so that is very common within the types of structures that we use in zero-knowledge proofs. There's a link there if you want to try out some operations on finite fields. I think they're very straightforward. They're quite easy to understand generally. Just the idea that we've got a finite set to start with. That set is a set of integers, and then we have two operations that we can do on those integers. Okay. And as I say, typically we would have a prime number as our as the mod that we're doing our arithmetic with. The order of the field is the number of elements. If it's going to be a finite field, then the order is going to be a prime number or the power of a prime. This is needed because for the idea of getting the multiplicative inverses to work. That's why it has to be one of those. Okay. Generators work in the same way that I've just said. So we can take a generator, and for example, if we're thinking about the multiplication operation, we can just keep multiplying that generator by itself. So we're taking it to various powers, and then that will end up giving us all of the elements within our group. And a simple example of that is if we have the set of integers here, we just got 0, 1, 2, 3, 4. We can use that as our finite field, and then we can, from that we get the generators 2 and 3, and because those two values will give us the all of the elements within our set. And sorry, we sometimes remove 0 from our set when we're talking about finite fields. Okay, so that's just a little bit about some of the terminology about mod arithmetic and groups and fields, because you will, if you're reading papers, you will hear about all of that. I'll go on now to talk a little bit about complexity theory. So this again is just to cover it in a very high level, not going into very much detail at all, but it is useful to know because this is an area really, I guess, that maybe zero knowledge proofs came from, or part of them came from at least. And also some of the terminology that you hear about when we're talking about zero knowledge proofs, particularly when we're talking about comparing zero knowledge proof systems, comes out of complexity theory and how we look at problems. So complexity theory is talking about how it's looking about at problems that we want to be able to solve, and it is looking at how difficult that is. And particularly a couple of aspects we look at. One is if you have a certain problem, how difficult is it to find a solution to that problem? But also, if you are given a solution to a problem, how difficult is it to verify that that solution is correct? And we often talk about it and look at the difficulty in terms of the time it would take to either solve a problem or to verify a problem. Also, we sometimes talk about the space requirements. And if you're thinking about this from a computational point of view, this would represent, for example, the amount of memory that would be needed for some program to be able to either solve or verify a particular problem. And when we talk about it, we look at it in terms of the size of the problem. And defining that is a little bit loose, I guess. I'm not going to say that, go into that in a lot of detail. But I can give you some examples, and it will hopefully make sense about what I mean by the size of the input to the problem. So the classic example for this is, I think, the traveling salesman problem, where we're talking about somebody visiting a number of cities. Maybe they're trying to go to a number of Web3 conferences, and they have to travel between a number of cities. And the problem is to try to work out what is the most efficient way of traveling between those cities. And particularly if you come up with a particular route, is to answer the question of, is this the most efficient way of traveling between these cities? Is it the shortest route between these particular cities? And in this case, the size of the input to our problem would be the number of cities. Excuse me. So if we say, if we, for example, talk about 3 cities, then working out the route or verifying that a particular route is optimal is quite straightforward. With just 3 cities, that's going to be quite easy. But as the number of cities grow, that becomes much more difficult, and it could be seen as intractable eventually. It could be seen as something that we can't do in a reasonable amount of time. And what we do when we're looking at these problems, the mathematicians and the computer scientists have tried to group problems into various classes, and based on how they how much time is needed to solve them or to verify a solution. And we do find that problems can be classed together. They do have similarities in this way. And the simplest class is one that is called polynomial. And what this relates to is the fact that for a particular size of input, if we represent that input by n, then the time taken to solve this problem would be proportional to n to the k. So where k is some constant, usually it's relatively small. But if that's the case, if our problem can be solved in a time that's relative to n to the k, then we say that's solvable in polynomial time. And these are seen as being reasonably tractable. That's seen as being something that we can do reasonably. If instead the size taken, or sorry, the time taken to solve the problem varied according to some power of n, then that would be much more difficult. That would be, that would grow much more quickly as n increases. And so those types of problems would perhaps not be seen as being tractable. Okay. And strictly speaking, when people talk about these, they phrase them as what is called a decision problem. So this is a problem that has a yes or no answer. So it could be, is this the optimal route for this, for traveling between these Web3 conferences? And as I say, we try to group our problems into classes according to their behavior and according to how difficult they are to solve or to verify. And what we find is that we come up with something like this, that we have some different classes: P, NP, NP complete, NP hard, and many others. There is an outstanding problem in maths and computer science, whether the classes of P and NP are the same. I won't go. I don't know the solution, and I don't think anybody can, and certainly nobody has been able to prove it so far. It is thought that they're not the same, so I'm going to assume that they're not the same. And so we're looking at this diagram on the left-hand side here, where the polynomial problems, as the ones that I've just spoken about, where these are, relatively easy to solve or to verify, are seen as being different from the NP problems, which are this larger circle that you see here. So having said that, well, what do these classes mean? What do I mean by these? Well, P typically means, P means that we can solve these in polynomial time. So as the size of the input to the problem increases, then the time taken to solve that is polynomial, or to decide or to check the solution is polynomial. And then NP is the class where to check the solution is polynomial. So if you have a problem in NP, then and someone gives you a solution, then you can check whether that is a correct solution in polynomial time. And a good example of that is this thing of if you think of somebody having a key, some encryption key, and they've encrypted something. If you try to work out what that key was, that's going to take you a long time. It's not going to be simple. But once you have the key, checking that is the correct key is not going to take you very long, because you can simply try to decode some plain text and you will see whether that is the correct key or not. So that kind of intuition is quite useful if you when you're looking when you're trying to think about what is involved in an NP problem. And then we have other classes as well. I won't go into those in detail. We don't need to know so much about those. One of the relevant points, though, I think, is the idea of transforming problems. So there is this property which seems quite fortuitous, that if we have a certain problem, we can transform it into another problem. And what this means is that if we can solve one of the problems, then we can transform it. If we have a solution to one problem, then we can take another problem, transform it to the original problem, and that gives us a solution. And that idea is what is behind this, the point of the NP complete class. And this transformation has to be done in a reasonable time. Again, so we have this idea of being that happening in polynomial time. And as I say, what people have found when they look at the problems that exist is that it is possible to group these things into these types of classes. And there's some links there if you want to look at it in more detail. What is particularly interesting to us, I think, is the idea that if we have a problem in the NP class, then it has been found that gives us or can give us a zero knowledge proof, or we can get a zero knowledge proof from that problem, which sort of brings that back to our sort of starting point, or where we want to be, because that's what we're looking at. We want to know about zero knowledge proofs. So if we have a problem in NP, we should be able to create a zero knowledge proof from that. And what that means is that we should be able to get a solution to that problem and prove that is a correct solution in polynomial time. And if you read about zero knowledge proofs and the types of systems that are built, then you'll see that this idea of being able to check the solution to something in a reasonable time is very important. And it's the terminology used for this is succinctness. So people talk about having a succinct proof, or being able to verify a proof in a succinct time. And this is an essential aspect of zero knowledge proofs. The idea that we could, for example, do some computation and then check the result of that computation in a much shorter time than it took to do the original computation. So what we can do is we can do some computation, we can create a zero knowledge proof of the correctness of that computation, and then we can check that proof in a very short time, so in much shorter time than it would take to redo the whole computation. And this is one feature of zero knowledge proofs that is extremely useful. And this comes back to the ideas around these complexity classes, that we can check the solutions that we have from an NP class in polynomial time. And so that's the kind of the tie-in between the complexity classes and the zero knowledge proofs. Now, another type of complexity class that we have is called IP, the interactive proof class. And this is really the starting point, I guess, of zero knowledge proofs. The idea that traditional mathematical proofs started out being done in a way that where you would go from one statement to the next, and you would finish with some statement that you were trying to prove, but there was no interaction. And what certain people then thought about was, well, perhaps we could introduce some interactivity into this process, where the person creating the proof is the prover, and then they're wanting to convince a verifier of this proof, and there is some interaction going on. They also bring in the idea that this process could also include some randomness, that the verifier, the person who is checking that this proof is correct, could introduce some randomness into the process as well. And so that was kind of a starting point, I guess, for where zero knowledge proofs came from. Also, the idea that they were thinking about people proving and verifying proofs, but started to think about, what if these people were not honest? How can we be sure that the prover is giving us a correct proof? And how can we be sure that a correct proof will be accepted by a verifier? If you want to find out more about that, there's some really good videos by Alessandro Chiesa, who has done a lot of work in this area. So I recommend you having a look at those. Okay. Now, another reason we want to know about or the complexity classes are useful is some of the notation that you get from them. And this is the big O notation. And this is a way that we can quantify the complexity of a particular problem. And it's a notation that you typically see when you're talking about complexity classes, but it is also very widely used when we talk about zero-knowledge proving systems and we're talking about sizes of proofs, or we're talking about the time taken to verify proofs. And it is the big O notation is talking about, in the worst case, what would be the time or the space taken to solve a problem or to verify a problem in terms of the input. So if the input is represented by n, then we may say that we have a problem, or we have a system where the time to verify the solution to the problem is O n squared, which would mean that as n increases, the time taken to verify that is proportional to n squared. This is represented pictorially here or graphically there, but also this table, which is a little bit old, but it gives you an idea. Excuse me. Of comparisons we can make between different types of proving systems using this notation. So, for example, if you look at the proof size, this is the third row down here, we see that for a snark, we have big O of 1, which means that we don't actually care about the size of the input. It's a constant proof size, no matter how big the input to our proving system is. No matter what the size of the claim we're trying to prove, the proof size is going to be constant. Whereas with a Stark-based proving system, it is quite different in that it is related to the log of the input, or some polynomial of the log of the input, etc. So this just gives you an indication of how we use this notation when we want to compare different types of proving systems. So you will see this used quite widely to give you an indication of the strengths and weaknesses of zero-knowledge proving systems. Okay, so that's a little bit about complexity theory and how we talk about it. I'll move now on to some objects that are widely used, well, in ZK, but also in blockchain and in cryptography. And these are elliptic curves. So these are curves that are represented by particular equations. They're usually of this type of form, something like y squared equals x cubed plus ax plus b, where a and b are some constants. And you can draw out these curves, and the mathematicians and the cryptographers will produce, they will pick values of a and b and produce curves, and they will give these curves names, and different curves that are used for different algorithms and for different blockchains will have different names, and they pick these constants to give the curve certain properties, properties that are useful. And one of the reasons that elliptic curves are particularly useful is that the points on the curve can form a group. So if you think about you've got your x and your y values, and you take certain x values, and you've got your a and your b, you've already decided on those. Excuse me. And this will give you x and y values for your curve. What you'll find is that for some curves, the points on the curve, these x's and y's, will have the group properties. We also need to have an extra point that we call the point at infinity, which is the identity element for our group. But that is a very useful thing that these points can do. And if you remember, if we go to call this a group, then what it means is that for the group operation, then if we take two elements and we do the group operation on these elements, then the result of that will also be in the group. And what that means is that for an elliptic curve, we are usually talking about adding 2 points. So our group operation is addition. And so if we take 2 points on the curve and we add those together, then that will give us a point that is also on the curve. The result of that will also be on the curve. Now, the way that we do that addition is not done maybe in a straightforward way. We don't, for example, just add the x values together and the y values together. There is a specific way that we do this thing that we call addition. But even so, there is this important point that when we do this operation on 2 points, then the result of that is also going to be a point on our curve. And then the other group features also apply. So the fact that it doesn't matter which order we do this in, and we can add further elements, and again it doesn't matter the order that we do that in as well. And we also have this identity element, which for an elliptic curve is the special element that we introduce called the point at infinity. So it's a very useful thing that the property that these curves have, the fact that their points will form a group. And you often see this represented by this type of thing. So here you can see the curve is this red line, and what we're doing here is doing the addition of points P and Q, and the answer here is given by the point R at the bottom of the diagram here. So this is there are ways that we can work out how to do this geometrically, but yeah, it is the point. It is a fact that we end up with a point that is also on this curve. Okay. Yeah, and this is very useful. We use this in cryptography. It's as a basis for creating public and private key pairs and for doing signing algorithms, etc. So the elliptic curves are very useful. They're useful as well. We do have options. We could use other kind of mathematical structures, but elliptic curves give us do this quite efficiently. When we're looking at something like a public-private key pair, this means that the values that we get are often quite short. We don't need, for a certain amount of security, we don't need such large numbers. Okay, but as you can see here, we have curves with different names, which the mathematicians have just tried out various values and come up with an equation that gives them certain properties that makes them maybe quite efficient to do some of these operations. And there's some listed out there. So you can see particular curves used by, for example, Zcash. We do have different types of curves. We have Montgomery curves and Edward curves. So the Edward curves are slightly different, but yeah, both of those can be used. I should say, I'll go on to scalar multiplication first. So I said that on elliptic curves, we're talking about adding 2 points together, and we have a way of defining what we mean by addition. But we don't necessarily have a way of doing multiplication. And I said that, this is a group operation. So we're defining this for just one type of operation. So, that operation is addition, but we don't have a way of doing multiplication. How we can get around that, though, is to just repeatedly do our addition. So we define that then, saying we have this thing called scalar multiplication, where if we take a point and we add it to itself a number of times, then that is the equivalent of doing some multiplication. So with this example here, this formula here, we say we want to effectively do a scalar multiplication of our point P, and we want to multiply it by K. And so what we do is we take P and repeatedly add it together K times, and that will give us the scalar multiplication of P. So it's a way of getting around it because we only really have the operation defined for addition. We don't have a way of defining that for multiplication. Another term that you will come across is the thing called a root of unity. And this is used, I think it's used more generally in maths, and it is often used to talk, is used to do with rotation and sort of transformations of elements. We use it in ZK often because this is a way of when we want to index things, rather than indexing something going sort of 0, 1, 2, 3 and doing the normal counting numbers, we often index things by these things called roots of unity. And the way that we think about them from an elliptic curve is that if we take some point and then we do this scalar multiplication a number of times, if the result of that is equal to our identity element, then that is called a root of unity. That point is then called a root of unity. Here we say this is equal to 1. I guess that's because that's sometimes seen as an identity element. I think perhaps more generally that will be the case. With elliptic curves, we will be our identity element is denoted as O. Excuse me. This is slightly confusing, not to be mixed up with the big O notation. Okay. Now, sorry for my voice. Visualizations of elliptic curves. I've shown you this. This is a nice, easy to look at visualization of a curve, but in this is not done over a finite field. This maybe is over the real numbers or maybe rational numbers. But you would, this is perhaps slightly confusing because when we're using elliptic curves in zero-knowledge proofs, we will be using a finite field. So this would be a field of integers with a maximum value. And if you look at, you see what that looks like, if you plotted that, you end up with a curve that looks like this. So here we have a field of integers where we're taking, we're doing mod 191. So our to give our set of integers, and then the elliptic curve is then calculated over that finite field, and using this particular equation to give us a curve. So obviously it's not as easy to look at, but that is what if you actually plotted it over a finite field, that is the type of representation that you would see. So even though this type of representation is easier to look at, do bear in mind that that's not done over a finite field. Okay. And there are further details. There's a video there that gives you further details about elliptic curve arithmetic. Okay. Now, a property that we need with a zero-knowledge proofs is called pairing. And this is to do with groups. It's a kind of an operation that we can do on pairs of groups, and it's particularly useful. Certain types of zero-knowledge proving systems rely upon their pairing being available, particularly on the fact that we would have elliptic curves whose group, the group of points on those curves, allow pairing. And what pairing is some type of function. So I've represented that here by E, which is between three groups. So you have two groups which take as an input, sorry, you have a function E which take as an input elements from two groups, and then the result of that would be an element in a third group. So this could be, for example, you may have some elements that are from two different elliptic curves. Those would be the inputs to your function, and then the result of that would be an element on a third curve, for example. And if you've chosen your elliptic curves carefully, and they allow pairing, then we get certain properties from this. The non-degeneracy one is just to say that it is a non-trivial thing that we are doing. And then the important one is the fact that we can get some useful properties around the function that we do with that. And what all of this leads to is just saying that for all elements in our input groups, for some particular elements A and B, then we get this result here that really what it's saying is it's the order that we're doing the function and the group operation doesn't matter. So we get this kind of result we've got here. So P and Q here would be the inputs to our pairing, and you can see that there's an equivalence here where we can add. We're effectively adding. We're doing a group operation on the input, and that is the same as doing the multiplying the results of this function together. So it's just a useful property that we have when we have pairing, but that this gets used more widely within when we're doing zero knowledge proofs. Okay. Question: how does P relate to the groups? So in this case, so if this is the lowercase p that we have with the field description I have here, the Z lowercase p, that would be the prime number that is whether we're doing mod. We're taking mod to when we're doing our arithmetic. The uppercase p here is a one of the elements, one of the points on our elliptic curve. Okay. All right. So yeah, so that's just a general idea about pairing. So you will come across pairing. I'll talk about it a little bit later on because some things rely upon the fact that we can do pairing between elliptic curves. So one thing when you start to dig into zero knowledge proofs, you find is that it all boils down to polynomials. Polynomials are used really widely, which I think is quite fortuitous because polynomials are relatively simple things, and we've probably come across these before. You'll have done some manipulation of polynomials. When you were at school, you'll have looked for solutions of polynomials. You've found roots of polynomials. You may have added polynomials together, etc. So they're not a very difficult concept, but they're very widely used in zero knowledge proofs. So assume that you're kind of familiar with the form of them generally. We have this kind of form where we have a variable here. Our variable is x, and we raise it to certain powers and multiply it by certain coefficients, and then that gives us our polynomial. You can have polynomials in more than one variable, so they could be multivariate polynomials as well. So this one here is a univariate polynomial. We're only using x, but you could have multiple variables. You could have x's and y's and z's in your polynomial. But they are very useful, and they can contain a lot of information. And now, even though you might think, well, this polynomial here is relatively small, there's not much information in that. The point is that when we use polynomials in zero knowledge proofs, we have very large polynomials. We have polynomials with many, many terms, tens of millions of terms, for example. And so they can hold a lot of information. Another thing that we do with polynomials is that we put them together and we build up relations between polynomials. And then that can be very powerful, because if we have some equation like this, where we say we have three polynomials, A, B, and C. If we say that in general A plus B equals C, then that means that that is true for any value of X. So which is what I've listed out here. So that means that A of 0 plus B of 0 equals C of 0 when X equals 0, etc. So if we can build up polynomials and we can put them into these kind of relations, we can get some very powerful things happening. The arithmetic on polynomials is relatively easy. There's a link there to an article about that, but it works kind of in the way that you would expect. And the other thing you will have probably done in your maths classes at school is to look for the root of a polynomial. What that means is when we evaluate a polynomial at a certain point, so for a certain value of x, if we evaluate 3x squared plus 4x plus 3, if there is a value of x for which that evaluation is 0, then we call that particular value of x the root of that polynomial. And you probably have done that many times in your maths classes, but it's a useful thing, and we do use that also quite widely in zero knowledge proofs. We can talk about polynomials dividing other polynomials. So you could have a relation between polynomials where you have b times c, so b and c are both polynomials, and they result in a polynomial a, or equivalently, you could say that a would, that b would divide a to give us our polynomial c there. Now, what is another technique that is used widely with polynomials is the idea of factorizing a polynomial. And this relies upon the idea that we know the root, or we know a root for a particular polynomial. Now, I'm going to talk now about the degree of a polynomial. The degree of a polynomial is just the highest power of x within that polynomial. So as you add more terms, then you're increasing the degree of the polynomial. Now, if we have a polynomial, so if we have a polynomial here, I'm saying the polynomial is p, the variable is x. We're going to say the degree of that is n. So our highest value of x within that polynomial is x to the n. What we can do if we know a root of that polynomial, so if we say that the root is r, then what that means is that if we take x to be equal to r, so if we evaluate the polynomial at the value r, then that evaluation is going to be equal to 0. And if we know that, then that means that we can refactor our polynomial into this type of form. So we can take out a term, x minus r, and then from our polynomial, and then the rest of the polynomial, or the result of that, is then going to be this other polynomial, q of x. So what I'm saying is that p of x can be rewritten as x minus r times q of x, where q of x is some other polynomial. But it is just the fact that we can rewrite it. We can refactor our original polynomial like that. And the degree of this polynomial q that we have got by rewriting our original polynomial is going to be one less than our original polynomial, because sort of intuitively you can see that will be the case, because we've taken an x out of our polynomial p into this term at the front here, x minus r, and so the terms within q of x are going to be we're going to need 1 degree less, because to get back to our original p, you will be multiplying x by q of x, and so you would have to have the highest value, the highest power of x within your q of x to be 1 degree less than it is in p. Okay, so that's just a useful thing that we can do when we have a polynomial where we know a root of that polynomial. But again, this thing is used very widely within zero-knowledge proofs. And it is used particularly because we express the claim that a prover will make. We often express that as a set of constraints. And the way that we express those constraints is to say that a certain polynomial would be equal to 0 at a certain point. And so once we know that, then we can easily manipulate polynomials and rewrite them in this refactored way. And this helps us. This is a useful technique that we can use when we're creating our proof, and it's useful because it helps to hide details of our proof. So this helps with the zero-knowledge aspect as well. Now, a fundamental idea behind the way that we do verification of proofs is this thing called the Schwarz-Zippel lemma, which is often expressed as different polynomials are different at most points. And why this is useful in zero-knowledge proofs is that, and I'm going to speak very generally here, and what I'm going to say is in some ways not quite correct, but as a starting point, it's a useful way of looking at things. So as a starting point, you could say that what we often do with zero-knowledge proving systems is to encode the proof that or the claim that the prover is making into a polynomial. And then the verifier is going to want to check that is correct in some way. Now, we want our system to work in a reasonable way. We want the whole thing to be succinct. So when the verifier is checking the claim that the prover has made, we want them to be able to do that reasonably quickly. So our proving systems are often interactive, so the prover and the verifier will be going back and forth, but we want to try to reduce that. So we want the verifier to be able to check whether the proof is correct with just a few checks, just a few queries that they can make. And if we have the possibility that we've moved, or we've got our proof encoded in some way into some sort of polynomial, then if we think that the verifier may know what that polynomial should look like, or maybe what sort of features that polynomial will have, then this lemma becomes very useful, because what it means is that when we're checking the polynomial that the prover is supplying, then if they've supplied something that is incorrect, then we should be able to find it quite quickly, because what the verifier has is some indication of what the polynomial should look like. And if the thing that the prover provides is not correct, doesn't match what that polynomial should look like, then we should be able to find that out quite quickly. Because if the verifier says, well, okay, tell me the evaluation of your polynomial at a certain point, because of this Schwarz-Zippel lemma, what it means is that for most points that the verifier chooses, if the prover doesn't have the correct polynomial, then the verifier will see that very quickly. The verifier will see that evaluation is wrong, because the points where an incorrect polynomial would match a correct polynomial is very few. It is much more likely that the evaluations are going to be different, and that's all because of this Schwarz-Zippel lemma. Okay, but I am taking some liberties here by talking about the way that we're how we're encoding the proof, etc. But it's when we create proofs, and when we get the interaction between prover and verifier, we really do aim at we are trying to get things represented as polynomials, or often sets of polynomials. Okay. So that's just further other ways of sort of saying the same thing. Now, a couple of questions you might have about that. Well, you could say, well, why doesn't the prover just send the polynomial to the verifier, and the verifier could just check that? Why would they want to evaluate the details? This comes back to the idea of the succinctness. Well, 2 points. One of them is the idea of succinctness, the fact that the polynomials we talk about can be very large, and so it's not feasible to send the whole thing to the verifier. And there's also the zero knowledge aspect, that the prover is trying to hide details of what they're doing, because they don't want to give a lot of information away to the verifier, and therefore they don't they don't want to share all of the information with the verifier. So they're going to be they want to be able to share selective pieces of information, such as the evaluation of a polynomial at a certain point, and then we want that to be sufficient for the verifier to be able to decide whether that constitutes the correct proof or not. Another thing to think about as well is, well, if we had the coefficients of the polynomial, does that show us whether two polynomials are equal? And at this point, the fact that we're working with finite fields is relevant, because when we are evaluating these polynomials, because we're doing our evaluations with modular arithmetic, mod some large number, we can get things wrapping around. And so what this can mean is that polynomials that could look different in a finite field when we do the evaluation, they may actually evaluate to the same values. So polynomials work, they work a little bit differently in finite fields to how you would have sort of been used to them working, say, with real numbers. So just to make you aware of that. So I've spoken about polynomials and them having a coefficient form. And then also this idea that you can take that form and supply some value of x, and that gives us an evaluation. So that if we go back to this 3x squared plus 4x plus 3, we can say, well, what does this evaluate at x equals 7, for example? And that will give us some value. But there are two forms that we can think of polynomials as having. We can think of them as the coefficient form, as you've just seen, or maybe you could think of them as being evaluations, of being the points of being an x value, and then the evaluation of that polynomial for that x value. So if you plotted the polynomial on a graph, that is the form that you would see. And so you get this kind of representation. The red dots here would be are the evaluations at certain values of x, at x equals 1, 2, 3, 4, 5, 6. Sorry, a 0 as well. And when you evaluate that polynomial, you get these red dots. And then you can go between these two forms. So if you have the points, if you have these points on a graph, then you can get the coefficient form by doing something called interpolation. So that allows you to move from the points to the coefficient form. So if you have a set of points, you can find the polynomial that goes through those points by doing interpolation. One method of that is Lagrangian interpolation, but yeah, there are different ways to do that. And what you find is that the degree of the polynomial, or the degree of the lowest degree of the polynomial that you can find that will fit those points depends on how many points you have. And if you think about this, this makes sense intuitively. If you have 2 points, then you could fit a straight line through those points, and that is a very low degree polynomial. If you have 3 points, then there would be a curve through those points. So that is a 1 degree higher, and so on. So the more points that you try to fit your polynomial through, then the higher the degree you need, the degree of the polynomial that you need. So we have this idea then that we have 2 representations, and we can easily move between these 2 representations, either by doing interpolation or by doing evaluation. Okay, so yeah, so polynomials are used very widely in ZK, and what often, or part of the process, is that the verifier will be asking the prover to evaluate a polynomial at a particular point, and the point that the verifier chooses will be chosen at random from some very large field. So the finite field that we're working in will be of order maybe 2 to the 250, something like that. And the verifier will pick a random value from that and ask the prover to evaluate the polynomial at that particular point. And if we've designed our system well, then we should be able to, with just a few evaluations, so the verifier just picking a few random values and asking for evaluations of the polynomial, they should be able to confidently decide whether a proof is correct or not. And part of the way that can be done is using this refactoring idea, and that's what these equations here are all about. Is that if the prover is claiming that their polynomial is 0 at various points, so the points here x1, x2, up to x to the n, then the verifier can start to build up a polynomial of these kind of terms, so of x minus x1 times x minus x2, etc. Because of this, the fact that we can do a factoring of polynomials, and this is a technique again that is used very widely. Okay. Now, I've spoken about it so far as if the prover and the verifier were actually working with these polynomials, but there are problems with that, which I've kind of mentioned, but I'll go through them again. And that one of those is the idea of succinctness, and that is if the kind of polynomials we use in ZK, they have a lot of terms, maybe tens of millions of terms. And so if the prover was sending all of that information to the verifier, well, that wouldn't really be feasible. That's much too much information to be transferred, and also much too much to evaluate each time we want to check a proof. It would just take too long. So instead of that, and then the second point is that the prover wants to keep some information secret. That is the zero knowledge aspect of zero knowledge proofs. And so if they sent all of the details to the verifier, the verifier may be able to reverse engineer the process and somehow work out the secret that the prover has. So instead of dealing with polynomials directly, what we deal with are things called polynomial commitment schemes. And these are a way to represent a polynomial and to represent the evaluations of a polynomial, but in a very succinct way. Now, commitment schemes generally are widely used, and one example you've probably come across are hash functions, where we can take a commitment to a particular message by taking a hash of that message, and that will give us some value. And yeah, that is a commitment scheme. And there are different ones, but what we want is a commitment not to a message, but to a polynomial. And in particular, we want not only a commitment to the kind of the polynomial itself, the format of the polynomial, but also we want a commitment to the evaluation of that polynomial at certain points. But that is kind of related because we have this possibility of moving between points and coefficient forms anyway. But so for a polynomial commitment scheme, yeah, we want this idea of being able to commit to a particular polynomial, and then this giving us a nice small representation of that polynomial. It also means that if the prover in a ZK interaction commits to a particular polynomial, what that means is while this interaction is being done, they are committed to that polynomial. They can't change their mind partway through, which might help them cheat the verifier. So, which we don't want. So we want the idea that they, once they've specified a polynomial, that they are committed to that particular polynomial. And a commitment scheme generally has two properties. One of them is the idea of binding, which means when you commit to something, then you can't change what you're committed to. You are committed to that, and it can be seen if you've tried to change that later. The other property that some commitment schemes have is called hiding, which means that the output from this commitment scheme obfuscates the input. So we see this with hash functions. If you have a message and you hash that message, it's not clear from the output what the original message was. And this is quite useful for us as well. The idea that for the prover, they would like to be able to take their polynomial, which kind of represents an encoding of their proof, and then get a commitment to that, which would hide details of that polynomial from the verifier, because they don't want the verifier to know all of the details. And that's what a polynomial commitment scheme will give us. Okay. And one property, this kind of goes back to the properties I was talking about when I was talking about the Schwarz-Zippel lemma, etc., is this idea that if the verifier is checking the polynomial, if they check it at a particular point, then if they have a set of polynomials, and if we say we have some polynomials, we want them to be in a certain relationship for each other. So what I'm talking about here is this thing here. So I'm saying that we have polynomials P, Q, R, and S, and we have some idea of the relationship they have to each other. What we could say is that if that is true for one value of Z, then we can generalize. The verifier can generalize and say, okay, I've chosen this value Z where this is true. Then this is probably true for any value that I could pick. And this is one of the useful features of polynomials, which means that when the verifier is checking what the prover has, they don't need to do too many checks. They can do this for a couple of points and then kind of generalize and say, okay, this is going to be true generally. Okay. Now, going back to the commitment schemes, the way that this tends to happen is we often use things like a Merkle tree to produce a commitment scheme. With a Merkle tree, this is a data structure where we have the leaves of the structure, the leaves of the tree are hashed together to produce the next node up, and then those nodes are hashed together to produce the next node up, etc., until you get to the root of the tree. You get the root node. And we can use a similar thing for polynomial commitment schemes, whereby the leaves of the Merkle tree represent the evaluations of a particular polynomial at certain points. So it could be that the first leaf in the tree represents the evaluation of that polynomial at point x equals 0, and then the next one is evaluation at point x equals 1, and so on, for all the points that you would want, you would need evaluating. And you could use that as the basis of a commitment scheme. Okay. I've spoken about the binding and the hiding properties, so I won't say that again. Now, within ZK, different types of polynomial commitment schemes have been invented, and these rely on certain assumptions. So you can see the different types here. So the commitment schemes themselves are, say, Fry, KZG, the IPA, and Dark. The things at the bottom here, these are some of the proving systems that they have led on to. Now, the next few diagrams are taken from the ZK study group video where Justin Drake talks about these. It's a great video, or it's a set of videos. So please do have a look at those. I've just taken some details just to give you an idea how some of these commitment schemes compare to each other. So if you say that we need a commitment scheme when we're doing zero knowledge proofs, they're very useful to have. I haven't really said how we create these, but people have worked out certain schemes that we can use. They've worked out the cryptography behind them, but they have different assumptions underlying them, and they have different properties. I'll just quickly talk about some of these properties here. So again, this is from the slides from that the study group. Now, what you'll see, the across the top here, these are the types of commitment schemes we have. So the ones that are based on a hash function, this is the Fry commitment scheme. This is the basic scheme that is used for the Stark types of zero knowledge proofs. The pairing group, these are, for example, the KZG commitment scheme, and these need elliptic curve pairing, and so this is the pairing that I spoke about earlier. There are different types. I won't go through the other types, but there are different types of schemes you can have. But I'll just describe quickly the properties that are being compared here. The first one is called transparent. This is related to the way that we create our scheme. When we're setting up our zero knowledge proving system, we may need to do some kind of setup. If it is transparent, as is the case with the hash function, that means that the setup is public. Everybody can see all of the information in the setup. We don't have to hide anything. For the pairing group schemes, such as KZG, it is not transparent. There are certain things in the setup that need to be hidden. Otherwise, cheating could occur. And so that's why this is colored. Well, it's meant to be red, I guess. So they're not transparent. Succinct, this is really to do with, has a very precise term. So it just means really that the hash function, the commitments you get from that are much smaller, are small for the size of the input polynomial that you're committing to. So for the hash function, these are smaller. For say the pairing group, they tend to be bigger, so they're not as succinct. For the unbounded, this is about the size of the input. The hash function can handle any size of input. The pairing group, there are various restrictions about that. They will not work above a certain size. Updatable just means that we could switch out our hash function and replace it with a different one, and that would still work. For the pairing groups, this is more difficult. And then the one that people are perhaps most interested in is the post-quantum. Because this is based on a hash function, this will still work once we have quantum computers. The ones based on a pairing group may well be broken or may well be broken by the algorithms that are possible with quantum computers. Okay, I won't go into the rest of the items here because we are getting short of time, but it just gives you an idea of the how efficient or the sort of the time taken for different types of proving systems. This final one here is talking about security. We typically target what is called 128 bits of security when we're creating these systems. This just gives you an idea of how easy it will be to brute force these systems. And 128 bits is seen as being an adequate amount of security. The size here that you get, this where we've got 256 bits here, 381 bits. This is the size of the commitment that the commitment scheme will give you. The term lambda here, this is a security parameter that you pick when you're building your scheme. I think you can pick this to give you less security, and that will give you better performance. For example, in terms of how long it will take how long it takes the verifier to verify a proof. But obviously, but yeah, usually you're targeting 128 bits. Okay. All right. I'll move on to a different topic now, which is error correction. And this is used particularly with the Stark-based proving systems. And but again, this idea is quite general. It's not just, this was invented as a general concept, not for zero-knowledge proofs particularly, but it's around the concept of redundancy. And if we start with a message and we give it some redundancy, that gives us a thing called a code word. And one particular way of doing this is called Reed-Solomon encoding. And this has been widely used, and is used, for example, in media. If you have some media, I think things like DVDs, the way they are encoded, there is redundancy built into them using Reed-Solomon encoding, so that when they are being read, if there is a mistake, if they're read incorrectly, that the original message can be reconstructed because of the redundancy present. And the way, we add the sort of formally they talk about the idea of having symbols, and then you add in extra symbols as being the redundancy. And then there is a formula which you can use to work out if how much leeway you have. If a certain number of your symbols are lost or are incorrect, what is the maximum that you can allow to be incorrect and still be able to recover your original message. So there's details of that there. Now, the way that Reed-Solomon does this is that they use polynomials to do the encoding. And so you encode your message as the coefficients in a polynomial, and then you can use evaluations of that polynomial to give you the redundancy for that. So that's what this is saying here, is that the message, the original message you want to encode, is given by the coefficients in a polynomial. Once you have that as your message, then you can evaluate that at certain points. And if you evaluate that at a lot of points, that's going to give you extra redundancy in your message. And given those points, because we know how to do interpolation, we can take those points and recover the original polynomial. And if we have extra points, extra redundancy, this means that even if some of those points are incorrect, we should be able to have a way of reconstructing our original polynomial. And once we have that polynomial, that gives us the coefficients, and those coefficients are our original message. The way that we can add redundancy is sort of shown graphically here. The fact that we could create a polynomial from a small number of values. So we've got x1 up to xd here. But once we've created our polynomial, then we can evaluate it outside our original domain. So we can then evaluate that polynomial at many other points, and then that gives us redundancy within our system, because we know, and we can either we can evaluate it because we know the formula for our polynomial. Okay, and if we have a certain number of points, we can reconstruct our polynomial. And once we can do interpolation to reconstruct it to get the coefficients. Once we have that, then we can deduce all the other values within a particular domain. Okay. All right. So that's you see this within Starks, particularly because we do some encoding of our proof effectively, and then we want to know whether that encoding is correct, and we use Reed-Solomon for that. Okay. Now, I'll finish off with this, the thing about the inner product argument. So this is something that is used in a particular type of polynomial commitment scheme, but you may well see it being talked about. But again, it's just a general mathematical concept, and it's based upon the way that we manipulate vectors within the way that we can multiply them, or the way that we can combine vectors. And if we combine them to give using this inner product, that gives us an idea of how similar the vectors are to each other. And effectively, it will tell us whether two vectors are perpendicular to each other. Perhaps I just say, remind you about vectors if you've forgotten about those. So a vector gives us not only a magnitude but also a direction. So these are often sort of denoted sort of on a graph as being a line with a certain direction. And if you think about various lines on a graph, and you think about if you had two lines and you wanted to know whether they are perpendicular to each other, then you can do this inner product of the vectors, and that will give you an answer to that. That will tell you whether they are perpendicular. So this dot product is the way that we do this inner product, and so that's just a general way that we can combine two vectors. We'll do an operation on two vectors. So the vectors here, A and B, are represented. This little arrow above them is showing that they are vectors. Okay. Now, what we can do, we can take this further by, if you have this vector A here, which has A0, A1, A2, etc. And then for B, instead of being these B values, if we say that we're going to have some Z value, but the Z values here are the powers of Z. So our B vector is going to be 1, which is Z to the 0, and then Z, Z squared, and so on. So taking the powers of Z. Then what the inner product of A and B would give us a polynomial evaluated at a point Z. So if you do the inner product, it gives you, sorry, the A values here would be the coefficients, and the Z is our variable, and then the inner product then will be the evaluation of the polynomial at a particular Z value. And this is used in certain ZK systems, such as bulletproofs, and it's used because we want to create a commitment to a particular polynomial, and this is done via elliptic curves. In fact, we can, if we have some points on the elliptic curve, G0 and G1, we can then create a commitment by adding these values, as you can see there, to give us our commitment C. And what it means is that this commitment means is that we couldn't have other numbers that would give us this commitment. So this is the equivalence of saying it's a collision-free hash function. So once we have that commitment, it means we couldn't then change our mind and say, oh, actually, I want to provide these values instead, and these values would form the same commitment. No, once we have a certain commitment, only the original values will give us that commitment. So if we start off that as being points, if instead we then take a vector, that will give us a commitment to that, and that is used in the bulletproof types of zero-knowledge proving systems. The way that is used is when we are checking this, and in fact, this technique is used more widely. Often what we do is we start with something fairly large and complex, and we break it down into two parts. And so in this case, with the bulletproofs, we break the vectors down into two parts, and we can check the commitment of these parts. We also see this in the Fry commitment scheme, for example, where we break things down into two parts, and then the verifier can check that has been done correctly, and check and quickly check that the different parts. We can sort of do this recursively. We can go on breaking things down further and further until we get to something that is very simple and can be checked very easily. So that is why we go through this process of breaking things down. It's a way of breaking down something that would be very complex, large and complex and difficult to check, into something that is much easier to check. Okay, so I'm out of time and out of notes, so I'll just quickly go through where you can go next. So this, as I said, was this came out of some talks that I gave where I wanted to introduce some mathematical concepts to help people when they're trying to learn about zero-knowledge proofs. But in addition to this, we do teach a number of boot camps and courses. So some of you will have attended the boot camps that we have done through Encode Club. There's a link to the boot camps there, or some of them there, because we teach a zero-knowledge proof one. We've also taught a ZKML course, but we do other ones as well. So those are the ones done by Encode. We also do our own courses as Xtrapy. So we have two coming up. We have a course about auditing smart contracts and a course about techniques to be used for arbitrage and MEV bots. So there's links to those courses there. Other links that you would find useful. We have there's the Awesome Maths repo where I've put, it's quite a small amount of links, but there's some links there that I think you will find useful. Particularly, I'll just show you this one. The Risk Zero Study Club is very, very good indeed. The Paul, who I think does most of the videos, is a very good teacher. He goes through a lot of concepts that are needed very well. So worth checking that out. He's got one video all about finite fields, which goes into much more detail and is better paced, I think, or slower paced than the quick description that I gave. So do have a look at that. I've also, there's a link there to some of our Medium articles around MENA and recursive proofs, and there's an introduction to ZKML. If you want to keep up to date with what we are doing, please join our Discord server, and we update that with announcements to tell you what courses are coming up. So yeah, you can see there. We can also provide other materials as well. Okay, so I'll finish there. Thank you very much for attending. I do apologize for the problems we had earlier. We hope that we'll be able to do another one on YouTube. I will publish, this is being recorded, so I'll get the link to that and I'll put details of that on our Discord server, and we'll pass it out on our socials as well, so you can get the recording to this. And you already have the notes, but if not, I'll just quickly display the QR code again, and that is the link to the notes there. So just go to bit.ly and Essential 2024, and you'll have these notes. Okay. Thank you again for attending. Thank you, Roger. That's very kind. Yeah, I hope you enjoyed that. I hope it inspired you to look into some of the maths and some of the aspects of ZK further. And I hope we'll see you on further courses. Thanks, everyone. Have a good day, and I hope to see you again soon. Thank you.